This research tests an unconventional approach to improving the low-power efficiency of the Autocycle engine, an approach that does not rely on any new materials or technologies. An Autocycle engine's highest efficiency results at near full throttle, full load conditions, and its lowest efficiency results at low load conditions near closed throttle. An engine should operate at its highest efficiency across its entire load range. A small engine having good efficiency can be made bigger by adding turbochargers, superchargers, and other gear to enable efficient operation at higher power, but at a cost of higher stresses and added complexity. An engine should have a design point set for its most efficient operation at its highest power and then be able to operate efficiently as a smaller engine at lower power. The model for my research is based precisely on that. My research takes a serious look at the Atkinson thermodynamic cycle as the best place to start. An Atkinson cycle engine's intake and compression strokes are shorter than its power or expansion stroke. It is the additional work extracted from the expanding gases during its power stroke that drives its efficiency higher. Named for its inventor, the original Atkinson cycle engine did this kinematically and in a single rotation of the engine's crankshaft. A similar cycle is achieved by closing an engine's intake valve late and into the beginning of its compression stroke. Closing the intake valve early does the same thing. These cycles run more efficiently, but at the cost of lower peak power plus the need for additional valve mechanism. My research presents a counterintuitive and much simpler approach to achieving the same thing by placing a flow restrictor after the carburetor to restrict the intake air flow. This might seem like introducing a loss and might also seem redundant considering the role of the engine's throttle, but the restrictor was kept as an independent variable by leaving the engine's governor and carburetor intact. The heart of my research is this: engineer a loss into a system in order to achieve a net gain out of the system. This research began more than a decade ago in 2007 and was continued in 2018-2019, showing promising results. Now I'll take you back to 2007 to view the research from its beginning. The hardware setup was simple, consisting of a generator set, some basic instruments like thermocouples and readouts, some pressure gauges, a graduated cylinder to measure fuel, a stopwatch to establish fueling rate, a resistive load bank to load the generator set, and some watt meters to accurately measure power. System efficiency was defined in terms of specific fuel consumption, or SFC. The units used here, milliliters of fuel consumed per watt hour, or milliliters per watt hour. Here's a close-up look at those instruments. First was to instrument and run the stock engine in order to establish a baseline reference for the research. This required some disassembly. A pressure tap in the cylinder head gives us some sort of composite pressure for the 4 engine cycle strokes. A 3/32 stainless steel tube and its fittings were installed. A static pressure tap was installed in the intake manifold. Thermocouples were installed to measure IAT, inlet air temperature, and also to measure EGT, exhaust gas temperature. The engine was reassembled. The engine was run on the load bank to establish the baseline calibration. The bank consisted of 6 individually selectable sections, 3 at 600 watts, 1 at 700 watts, and 2 at 800 watts. The load is resistive, so there's no need to consider power factor. Values in parentheses are watt meter values. The others are just element wattages printed on the light bulbs, like 100 W for 100 watts. This speed versus watts curve shows generator speed as the engine's governor responds to applied loads. Speed is expressed as hertz. Here's an animation of the baseline engine. The data shows the classic Autocycle characteristics with the most efficient performance, lowest SFC, at nearly full throttle, near the engine's maximum compression ratio, and its worst SFC at low power, throttle mostly closed. One thing in the data stands out, and that is the EGT is nearly constant across the load profile. However, this changes with the test engine. Few fundamental changes can be made to an Otto cycle engine, but two of those are combustion chamber volume and carburetor airflow. The cylinder head was again removed. Since the piston comes flush to the cylinder block at TDC, or top dead center, I only need to concern myself with the cylinder head's chamber volume. So stuff it full of clay, take it out, roll it into a log, and measure its displacement, which was determined to be 29 milliliters. The cylinder head's chamber volume was modified by machining the head, and its new displacement was determined to be 21 milliliters. The published compression ratio for this engine is 8.5 to 1. The volume change from 29 milliliters to 21 milliliters puts the static compression ratio at nearly 12 to 1. Attention now turned to carburetor airflow. This is where the counterintuitive part plays in. I placed a flow restrictor after the carburetor as mentioned. Two types of restrictors were tested. One was a restrictor plate, having 8 1/8 inch diameter holes arranged like you see, and the other type was a single hole restrictor with the same cross-sectional area as the sum of the 1/8 inch diameter holes in the restrictor plate. A second load bank calibration was performed for the test engine. The calibration showed a lower peak output power than the baseline engine. This second animation shows an engine running with a flow restrictor. At the test engine's maximum power, the data showed an increase in efficiency, that's a drop in SFC, over the baseline engine. It appears we have two different engines now, the baseline engine with a higher peak output power and the test engine with the lower peak output power, but both engines show their highest efficiencies at their respective full throttle, full load conditions. The baseline engine and the test engine with the 8-hole restrictor plate, that's this data, ran a stock fuel jet in the carburetor, while the engine with the single-hole restrictor, that's this data, ran an adjustable needle valve fuel jet in the carburetor. Earlier, it was pointed out that the baseline engine's EGT changed only slightly from the no-load condition to the full load condition, varying by no more than 22 degrees F, and not necessarily according to load. However, the test engine's EGT dropping 160 degrees F in accordance with what might be expected with a jump in efficiency as more work is squeezed out of the expanding combustion gases. Comparing data, we saw the single-hole restrictor engine build produced a maximum power of 1,864 watts. Simple interpolation shows the baseline engine used almost twice as much fuel to do the same amount of work. Thus, the justification for this project. The challenge and goal of increasing Otto cycle engine efficiency at lower loads and power seems to have been met, but only for an engine with a fixed restrictor. Even though the static compression ratio was raised significantly by machining the head, it is only an effective compression ratio and less than can be computed because of the flow restriction. The increase in compression ratio is only one factor contributing to the increases in engine efficiency for this particular cycle. It can be difficult to determine the dynamic compression ratio of this engine unless you use real-time pressure data acquisition and data logging gear. This is because valve open and valve close positions with respect to top dead center and bottom dead center are now only part of what determines the dynamic compression ratio. However, that caliber of data is not required in order to draw some general conclusions from this research. The composite cylinder pressures for both the baseline and single-hole restrictor engines show the test engine at 53 psi for its maximum load of 1,864 watts. Interpolation shows the baseline engine at 50.4 psi for the same load. The pressures essentially agree, but the 53 psi reading, being slightly higher, makes sense because the test engine's fuel-air mixture was adjustable via the carburetor's needle valve jet, allowing for leaner, hotter, and more efficient running. As a welcomed takeaway, the 2007 research suggested that any losses caused by the restrictors were negligible when compared to the net efficiency gains in the overall cycle. So what actually accounted for the increase in engine efficiency? Was the engine actually running in an Atkinson-like cycle? Fast forward to 2018-2019, the continuation of this research answers these questions. The research now focuses on reducing the power limitations experienced in the 2007 tests. It was decided to replace the fixed flow restrictor with a variable flow restrictor. This variable restrictor replaces the fixed restrictor at the same location. All of the original instrumentation now needed to be located or replaced. The load bank and watt meters did not survive the intervening years, so a new load bank was constructed, having the same load element values as the 2007 load bank, plus new watt meters. The same pressure gauges, stopwatch, and graduated cylinder were used, plus a new thermocouple readout. So here's a look at the 2018-2019 test setup. The new setup is very similar to the 2007 setup. Here is a new load bank. The load bank was identical in every important way. The sections were switched in and out using the exact same load combinations. The question begs to be asked, where will the variable restrictor be set during these tests? It was decided to set the variable restrictor at a position that causes the engine's governor to float the throttle near the carburetor's full throttle stop position for each load condition. This video shows that control point. Testing began. As said, the same load bank combinations were switched in and out during testing just as they were in the 2007 tests. The variable restrictor allowed me to overcome much of the power limitation issues, as can be seen in this side-by-side. Tests show the peak output power was still less than the baseline engine, but not by much. Two reasons for this. The recent tests were performed at a location 700 feet to 800 feet higher in elevation than the 2007 tests, and the variable restrictor still had an effect even at its full open position. A good practice is to duplicate test results in order to validate data and testing procedures. That applies here, especially considering the decade-plus hiatus prior to the resumption of testing. I attempted to duplicate the best of the 2007 test results, which was an SFC of 0.57 milliliters per watt hour. So the load bank combination of 4, 5, and 6 was selected just as in the 2007 tests. I was able to adjust the variable restrictor to a stable 1,818 watts, which is 97.5% of the 1,864 watt target. The SFC was essentially the same as shown in this side-by-side, which is interesting considering the usual effects of elevation on an IC engine. This test was important in another way. It showed that there is little difference in what type of restrictor is used: a restrictor plate with a bunch of holes, a single hole restrictor, or a butterfly valve restrictor. Viewers familiar with the various engine cycles will recognize the following engine cycle diagrams depicting the Otto cycle and the Atkinson cycle. The ghost curves on the Atkinson cycle diagram would correspond to different positions of the variable restrictor. These two diagrams are examples and are not derived from data. The following animations explain what's happening. This animation of a typical Otto cycle engine shows the intake and compression strokes to be the same as the expansion or power strokes. But the test engine animation shows the intake and compression strokes to be effectively shorter than the expansion or power stroke. The intake fuel-air charge volume is determined when the intake has been compressed to atmospheric or to carburetor inlet pressure. The charge volume changes with load. The variable restrictor affects efficiency to a greater degree at lower power and to a lesser degree at higher power. It's been the goal of this research to achieve exactly that. So the test engine is running in a variable Atkinson-like engine cycle. What's the bottom line? The following graphs tell all. The 2007 baseline engine red and the 2018-2019 test engine blue show roughly a 15% increase in efficiency at the high power end and roughly a 50% increase in efficiency at the low power end. Ideally, it would be preferred to have something like this, a constant SFC versus load, but you could only hope to achieve something close to what's shown with a different cycle, for instance, the diesel cycle. But I did get some interesting results when I used the variable restrictor to set a constant 50 Hz speed for each load condition. The SFCs wandered a bit, but I did end up with some good SFCs over 2/3 of the power range. A second test at 55 Hz yielded similar results. You can see this by their averaged slopes. I would say the challenge has been answered and the goal has been met. So, mission accomplished.